Hello, good afternoon, Smith.
Good afternoon, sir.
Others must be joining because of the previous lecture, na?
यस सर, कभी दिलीप सर का लेक्चर चल रहा है,
Okay.
इसलिए सर।
I hope they'll be joining soon, huh?
Yes, sir.
It's already 12 minutes past 3.
दिलीप सर लेक्चर दे रहे हैं सर, इंफॉर्मेशन दे रहे हैं सबको।
अच्छा,
मैं सर मैसेज कर देता हूँ ग्रुप में।
हाँ मैसेज कर।
ओके सर।
Okay, good afternoon, everyone.
Good afternoon, sir.
You can see the screen, no?
Yes.
Yes, sir.
Okay. So we ended up on this exercise. See, just prior to this, we had two expressions, one for the base and the other one was for an acid. And we were trying to understand what is the difference between the partition coefficient and the distribution ratio. Uh, Partition coefficient, C, is an expression where we are dealing with any substance which is neutral, which is unionized. So when a substance is unionized, we know that there is more chance of it getting extracted in the organic phase, and thereby one can have, high partition coefficients. But the moment that same species uh, is is possibly in a acidic medium or an alkaline medium, in that case what happens is part of it is ionized. So if part of it is ionized, naturally when we extract into any organic solvent, the the distribution would decrease. That means that constant would obviously decrease. So partition coefficient uh, is mainly concerned with any species in its neutral form, in its ionized form, and distribution ratio takes into account, as I can show you here, it takes into account the concentrations. Distribution ratio takes into account the concentrations of that particular species in both the phases in either acidic or alkaline medium, which is actually the case with real samples, So distribution ratio is actually the equilibrium constant which we generally look for when we are dealing with real samples. So, and based on which we could find that distribution D, it can be expressed for a base to be like base present in the organic solvent, that is B2, and base that is present in the aqueous phase, plus some of the ionized base or the protonated base which also would be present in the aqueous phase. Since it is a charged species, it has to be in the aqueous phase, and we know that in the denominator we express concentrations for all the species in the aqueous phase, whereas in the numerator we express all the species in the organic phase. So based on which we arrived at this kind of an expression for distribution, which takes into account what? It takes into account the partition coefficient, the ionization constant of the conjugate acid of that base, and of course the H plus ions or the pH of the medium. So based on which what we had at hand was, and similarly if there is a weak acid, we can have a similar expression based on similar workup. D is again is related to the partition coefficient, of course, the ionization constant and the pH as well. But the only difference here is that you don't find H plus in the numerator in the previous equation, but here you find pH in the numerator as well as denominator uh, um, in this case. So it all depends upon, if this is very less, Ka is very less of that acid, that means that acid is very little formed in the aqueous medium. Then what happens? If this is less, we can eliminate this in comparison to H plus, and then D becomes equal to K. That is what is, the expression for a weak acid. And based on this understanding, we had this a simple numerical which tries to show the extent of extraction uh, under different pH conditions. I'll just, though we did this last time, but I'll just repeat it. Uh, See, suppose that the partition coefficient for an amine B is K equal to 3. That means it is trying to tell us that this amine, when extracted under neutral conditions, the partition coefficient obviously K is 3. That is what it is found. That is, it is the maximum found, that is 3. And the acid dissociation constant of BH plus is Ka equal to 10 to power 9. That is the or the ionization constant of that conjugate acid. So this is the preliminary information which we have for a given base. Now they are going to apply certain conditions and would like to find out what would be the effect on this equilibrium constant, because K is also an equilibrium constant. At the same time, D, or distribution ratio, is also an equilibrium constant. The only thing is that one considers pH, one does not consider pH. If 50 ml 0.01 molar aqueous amine is extracted with 100 ml solvent, that means your aqueous phase is 50 ml and your organic phase is 100 ml. What will be the formal concentration remaining in the aqueous phase at pH 10 and at pH 8? Even without solving this problem, you can very well say that the extraction would be more in pH 10 as compared to pH 8, because at pH, this is a base. So of course it will be less protonated at pH 10, but it will be more protonated at pH 8. So if it is more protonated at pH 8, naturally the distribution would be less, and therefore the extraction would be less. So now, solving this problem, we have at pH 10, D will be equal to, we know this is the expression for distribution ratio for a weak base. So K into Ka divided by Ka plus H plus. We know K, that is 3, that is the under neutral conditions, and Ka is 1 into 10 to the power minus 9. This is the K value, and divided by again 1 1 into 10 to the minus 9 plus the H plus sign, or the H plus sign concentration, and if it is at pH 10, then it will be 1 into 10 to the minus 10. So if we just work out this, what we find here is that the D value is now 2.73. It is less than, this equilibrium constant is less than K value K, which is 3. It is, from this one can very easily surmise that KD will be either equal to or less than K. That is what one can surmise from this calculation. So now when we are going to find out the amount of extraction which occurs in terms of fraction, using that same formula, 50 ml is your V1, again 50 ml is your V1 here, and this is V2 100 ml, and this value instead of 3, because at pH 10 what happens, instead of 3 it comes out to be 2.73. so therefore we just replace K with D here, because this is actually the condition. So, and with the result, what we find here is that Q value is now is 0.15, and or we can say 15% of that amine is left in the aqueous phase. Q is a fraction which is in the aqueous phase. So it is 15% which is left in the aqueous phase. So that means 85% 85% was extracted into the organic phase at pH 10. If you just increase the pH now, if you just increase this pH to say about 12, you can find that even smaller fraction would be here, and even less would be would remain in the aqueous phase. So 15% is left, 85% goes into the organic phase. And if you just find out the 15% of the concentration of this is equal to 0.0015 molar. This is the concentration which remains in the aqueous phase after extraction. So this was the story for the first case, that is at pH 10. If we look at pH 8, what we find is the only difference is again, if we substitute here these values, 1 into 10 to the power minus 8, this comes out to be 0.273. It is even less. See the drastic change in the equilibrium constant or the distribution value. So it is now, instead of 2.73 in the previous case, it is 0.273 at pH 8. So if you substitute 0.273 here, keeping this constant, what we find here is that 0.65, no, 0.65 is the fraction which remains in the aqueous phase, or 65% remains in the aqueous phase, or in other words 35% goes to the organic phase. So there is the because of this drastic reduction in the value of a D from 2.73 to 0.273, what happens is that the amount which is extracted is even less. The amount which is extracted is even less. Only 35% is extracted here. In the previous case, it was 85% was extracted. So this problem was essentially meant to explain that for a weak base and to have a maximum extraction, it is important to have more alkaline pH or higher pH. 10, 11, 12, this should be the pH, so that there are very less chances of that base getting protonated or ionized, and it will remain essentially unionized at higher pH. Any problem with this? If you have understood, or rather have you understood this? Anyone?
No, sir.
No, sir. Okay. Thank you. Now, moving ahead, this is very which is only on which is on the similar lines, but as a separate part to find out how much percentage that is extracted. One can also find out the way in which we did in the previous case, but this is a different expression which will be which will try to explain slightly different concept here, and therefore we have this percent extracted. अब इसमें ये लिखा है, I'll just speak a little bit in Hindi also, because for the benefit of the others, the distribution ratio D is a constant independent of the volume ratio. Independent of the volume ratio. However, the fraction of the solute extracted will depend on the volume ratios of the two solvents. मतलब कहने का मतलब ये है, distribution ratio is independent. It is a constant, but if we increase the organic solvent, or if we increase the organic solvent volume, more solute or analyte will be dissolved or partitioned. That means the fractions would change. The fractions of solute that is extracted would change, whereas distribution ratio, which is independent of the volume ratio, would remain essentially constant. If a larger volume of organic solvent is used, more solute must dissolve in this layer to keep the concentration ratio constant and to satisfy the distribution ratio. So this tries to tell us that what is the difference between distribution ratio and the fraction which is extracted. Fraction of the solute will depend upon the volume ratios, and whereas distribution ratio would be independent of that. Now, again, we will arrive at a simple formula to find out percentage extraction. See, percentage extraction and distribution ratio. Distribution ratio is an equilibrium step, is an equilibrium state. It's a dynamic state. And whereas when we look at the percentage extraction, that is not an equilibrium step. It tries, now what it makes us understand, see, the fraction of solute extracted is equal to the millimoles of solute in the organic layer divided by the total number of millimoles. It does not state that millimoles of solute in the organic phase divided by millimoles of solute in the aqueous phase. It tells us the total millimoles of solute which were present initially, and that is how one can find out the amount which is extracted. So for that we need to know the amount which was present initially. For finding out the percent extraction, we need to know the amount which was present initially. And once we know that, and when we extract, some amount of substance would go to the organic layer. From that value and the initial amount present, we can calculate the percent extraction. And to find out this, what again they have said here is the fraction of solute extracted is equal to the millimoles of solute in the organic layer divided by the total number of millimoles. Now what this expression tells us is that we know that it is a concentration of the solute in the organic phase. O stands for organic, and this is the volume. So if we multiply the concentration by volume, we can get moles, right? See, concentration is moles by volume. So if we divide this concentration by volume, we will get moles or millimoles, whichever way. And if you want to find out the percentage extraction, we should know the moles which are extracted or the millimoles which are extracted and the millimoles which were present initially. Initially means the one that was extracted plus the one which is left after extraction. So it is a summation of millimoles of what was extracted and what remained in the aqueous phase. So if we know this, we can find out the percentage extraction. Of course, we can multiply by 100 to get percentage. Now, if we just divide this previous equation with SA V0, if you divide all the terms here, what we will get here is this D, again D here because this is same S0 V0. So if we divide by SA V0, so V0 will cancel and this will be equal to D, and this term would have only volumes. Volume of aqueous phase divided by volume of organic phase to find out. Now this is a simplified form. One can always use this form as well. One can always use this form also. But this is a simplified form which has the values of the distribution ratios as well. And if both the volumes are same, if you take 10 ml of volume aqueous phase and 10 ml of organic phase, then this will be equal to 1. So the further simplified form of this expression would be percent extraction is equal to 100 D upon D plus 1. If the volumes are same. It is generally doesn't happen every time, but if at all they are same, then it will be D plus 1. Now, this is again a simple problem which tells us, which makes us understand how can we find out the D values and how can we find out the percentage extraction. Now, this has the problem. The problem is 20 milliliters or 20 ml of an aqueous phase solution of 0.1 molar butyric acid is shaken with 10 ml of ether. So we know that the aqueous phase is 20 ml and the organic phase ether is 10 ml. So after the layers are separated after extraction, it is determined by titration that 0.5 millimole butyric acid remains in the aqueous phase. This much remains in the aqueous phase. What is the distribution ratio and what is the percent extraction? Now, if we can find out, see, initially it was 20 milliliters and this many molar solution of butyric acid. So we can easily find out the millimoles which were present initially. 20 into this 0.12. So if we can write this 0.10 moles per liter or millimoles per ml, either way. So this can be expressed as 0.10 moles per liter or millimoles per ml. So if you multiply this by 20, you will directly get the number of millimoles. So millimoles would be 20 into 0.10 will be 2. So now this is what is written here. We started with 2 millimoles butyric acid. 2 moles butyric acid. And what is mentioned in this problem is that after extraction, 0.5 millimoles remain in the aqueous phase. We started with this much remain. So how much must have gone? 0.15 millimoles must have gone. Okay. 1.5 millimoles must have gone. 2 minus 0.5 would be 1.5 millimoles was extracted in the organic phase. So the concentration of the in the ether layer would be in the ether layer, which is 10 ml. So if you divide this will be the concentration, because when we calculate D, it is the equilibrium constant. Percent extraction is not an equilibrium constant. Okay. So the concentration, to find out D value, what we know now is that 1.5 millimoles were extracted, but they were present in 10 ml ether. This comes out to be this many moles. And likewise, after extraction, the aqueous layer contained 0.5 millimoles and aqueous phase was 20 ml. So the molarity would be 0.025. So if we substitute these values in D, the concentration of that analyte in the organic phase divided by the concentration of analyte in the aqueous phase. So this comes out to be 6. So we know that D value is 6 for butyric acid, which is distributed between aqueous phase and the organic phase. Now, percentage extraction, we know that to find out percentage extraction, and if we know you into 100 into 6 D, here also D plus the aqueous phase divided by organic phase. Aqueous phase was 20, Organic phase was 10. So this comes out to be 75%. So there is 75% extraction when the D value is 6. And when we started with 10 ml of the ether and 20 ml of the aqueous phase for 0.1 molar butyric acid. Is it clear? Percentage extraction could also be, very easily found out that 22 millimoles था 1.5 चला गया ऊपर तो कितना बचता 2 में 1.5 तो 100 में कितना so it has become directly 75 or one can do this way and find out the value of 75 here. Either way you will get the same results. So in this problem what we have understood is, first thing, percentage extraction is not an equilibrium constant. Distribution ratio is an equilibrium constant. Distribution ratio is an equilibrium constant. And how to find out the millimoles of the amount which is extracted. So we just need to find out or determine through any technique how much was extracted and how much was present initially. And once we know these two, we can find out the percentage extraction. Is it clear? Richa?
Yes, sir.
Yes, sir. Is it clear?
Yes, sir.
Yes, sir. Good. Anyone else? Devarshi, I can see Ankita. Smith. Yes. Ankita said something. Yes. Okay. Okay, I'll just move ahead now. So this up till now, what we studied, again, I'll just repeat that there are two ways when we work with solvent extraction. There are two expressions, one dealing with the unionized species and the other dealing with the ionized species. And from one, we say that it is partition coefficient, and from the other, we say that it is distribution ratio. And which actually happens in real samples. So at the same time, we also know how to calculate the percentage extraction. But for that, we need to know the initial amount taken or the initial concentration taken. That is important when we are working to find out the percentage extraction. Whereas this is not, a mandatory thing when we work with equilibrium constants, because it works with, the dynamic concentration after extraction in both the phases. So up till now, what we have talked about, some molecules, organic molecules, which can be, extracted. And fortunately, we have these molecules are essentially covalent in nature, by and large covalent in nature. So there is a tendency that they would be extracted much more in the organic phase. So they would try to remain in the organic phase because they are neutral species, they are bulky species, and they are covalent in nature, they are less of ionic in nature. So this was all about the organic substances which we come across. Now, when we look at the inorganic ions or the metal ions, it becomes, it becomes highly unlikely that they would be extracted as such, because they are ionic species. So one can very well, comment on that, it will be difficult to ionize, difficult to extract metal ions from aqueous phase to organic phase. They would prefer to remain in the aqueous phase only. Now, to realize this, there are two approaches to extract metal ions. One such approach is ion association complex, formation of ion association complex. This is one approach which may not be widely used, may not be widely used, but there are certain very well-known examples, of ion association complexes whereby metal ions can be extracted in the organic phase. But the most widely used versatile approach is chelate formation, is a neutral chelate formation. See, we are trying to there are two things which we try to do in extracting metal ions. We somehow try to neutralize uh, the charge on the metal ion by forming a complex. One thing, and secondly, we want to make this complex more organic like, more covalent like, so that it doesn't prefer to remain in the aqueous phase. So from the inorganic character, we want to change it to organic character so that metal ions could also be extracted, of course, by chelate formation or a complex formation. Now there are few very, very versatile examples which tell us that how they can be ion association complexes can be used for extracting metal ions. Now, iron 3, we all have seen ferric salts. We know ferric solutions as well with different cations. Now, iron 3 can be quantitatively extracted. Quantitatively extracted means ज़्यादा से ज़्यादा quantitatively extracted from hydrochloric acid medium into diethyl ether. This is a very interesting case because where there is no complexing agent at all in neutralizing the charge on iron. What is the system? You take iron solution, but that is prepared in HCl medium, and then you extract into diethyl ether. Fortunately, the chloro complex of the iron, because it is HCl, it forms a chloro complex of the iron, is coordinated with the oxygen atom of the solvent, diethyl ether. Now, if you can see here, this is diethyl ether. Two ethyl molecules with an ether. So this is diethyl ether. This is FeCl3, FeCl4. It coordinates with two molecules of diethyl ether and forms a negatively charged bulky species. It forms a negatively charged bulky species. FeCl3 is fine. It is formed FeCl4 negative. FeCl4 negative is formed. That is obvious. But it coordinates with two molecules of diethyl ether to give a bulky anionic complex. At the same time, the H plus ions from the hydrochloric acid, they coordinate with the oxygen atom of the diethyl ether and gives rise to a positively charged species. Now, when these two species are present in that same solution, see, you have not added anything in this. You simply dissolve a solution of iron 3 ferric salt in hydrochloric acid medium, and then you extract into diethyl ether, and it gets extracted by, now this positive species coordinates with this negative species and gives rise to a very bulky organic kind of a molecule, organic kind of a species with negative charge closely associated with this positive charge, so that these two species stay together and give rise to a very bulky species which is more organic like rather than inorganic like. See, we are interested in extracting only iron, but what has happened here, that the solvent molecule itself tries to coordinate with the ferric chloride and the H plus ions, and thereby resulting in a very bulky molecule. And this bulky molecule doesn't prefer to stay in the aqueous phase. And the moment you shake with diethyl ether, it goes into the organic phase. And this is a very unique and very widely understood ion association complex example. Uh, this doesn't happen with everyone, with all the cations. This doesn't happen with all the binary or ternary cations, but it happens exclusively with iron, and this is how it remains stable also, because the stability of this species is also an issue, and this is relatively stable, and it remains stable in the organic phase, and thereby it affords separation of iron from aqueous phase to the organic phase. This was one very classical example. The other example is, these are all very versatile examples. I mean, I've just taken few examples from the literature where these are very specific cases. It doesn't happen with every ion, every cation. The uranyl ion UO2 2 plus is extracted from aqueous nitrate solution into isobutanol. See, again, you have taken uranyl salt, any uranyl salt, in nitrate solution, aqueous nitrate solution, small amount of nitric acid, and then you extract into isobutanol. What happens is two nitrate ions get associated with this uranyl ion, and this whole thing gets extensively solvated by isobutanol. This whole species gets solvated by isobutanol, and thereby, first of all, the charge is neutralized, and secondly, it gets solvated. It is surrounded by isobutanol. So it gives rise to a bulky organic species which contains uranyl ions, and this goes into the isobutanol solvent system, and this it is possible to extract uranyl ions. Otherwise, uranyl ions are very tough to extract. You need a particular complexing agent to complex it to neutralize the charge and then extract into the organic phase. But here we don't need to add any complexing agent. The solvent itself plays a vital role in extracting and in solvating the species which is generated in the aqueous phase. And the third example, आपने KMnO4 नाम सुना है. KMnO4 पानी में soluble है, पानी में soluble है. Organic phase में तो soluble है ही नहीं. That is not soluble in organic phases, water immiscible phases. But in this, one needs to add a complexing agent or a species to form an ion pair, and this species is tetraphenyl arsonium ion. This is a very bulky organic species. Now, when this is added to KMnO4 solution, it binds with or it interacts with the permanganate ion, which is negatively charged, and this is positively charged. So it itself, you can see there are 4 phenyl rings here, 4 phenyl rings. So it is more organic like, and therefore it gets extracted into the organic phase, into methylene chloride, dichloromethane. And that is how these are some of the classical examples based on ion association complexes. And the other very important example, which I've not mentioned here, but I can recall that, and that is crown ethers. Crown ethers are basically neutral species and they are organic species, organic molecules, and they don't have any specific functional group. They have a simple CH2O, CH2, CH2O, CH2, CH2O, CH2, CH2O kind of a structure. They do not have, any proper functional group with which anything can bind, directly can bind. But what happens is these are cyclic molecules. These are cyclic molecules and with a definite cavity size. With a definite cavity size. So in 1967, when people were working with this neutral, species or molecule, what they found was that KMNO4 we know is not organic solvent. It doesn't dissolve in organic solvents. It remains in aqueous phase. It is highly soluble in water. So what happened was that when they added this substance uh, to a solution of KMNO4 in aqueous, in benzene, they took this substance in benzene because it is not water soluble. It is soluble in organic solvent. So they took benzene at that time. Benzene is no more used now, but at that time they used benzene and they just added this to a solution of KMNO4 in water. KMNO4 we know is purple. So when they added that, after shaking this solution, because there are two immiscible layers, the entire aqueous layer was colorless and the entire benzene layer was purple color. That means MnO4 negative must have gone to the organic phase. So when they thought of what actually might be happening here, they found out that the crown ethers, which have a cavity, with the cavity which has O, CH2, CH2O, CH2, CH2O kind of a structure, this thing K, potassium ion, which is a alkali cation, it coordinates with the oxygen ions. It coordinates with the ether in that crown ether. And therefore, there was a positive charge. It gets coordinated with 6 or 4 or 5 oxygen atoms, ether. Now, potassium as such cannot go into the organic phase because it is positively charged. So there must be something more which is neutralizing the charge of the potassium ion, which is why we can see a purple colored benzene. So then they found out that the potassium is there in the cavity fixed up of these crown ethers, and the cavity and the size of potassium matches of 18 crown 6. Means there are 6 oxygens. 18 crown 6 matlab 6 oxygens, 6 ether oxygens. So potassium is coordinated with the oxygens, and to neutralize the charge, it takes MnO4 negative. So what happens is it becomes a bulky group now. It becomes a very bulky group. Bulky group means okay, you have an organic molecule like crown ether, you have potassium fixed in the cavity, and then you have MnO4 negative associated with this positively charged species of potassium with crown ether. And this entire species, this bulky species, now becomes more organic-like, less of aqueous. And therefore, this whole concept was thought of that this change in color from aqueous to organic, violet color from violet color for aqueous to the organic phase, that potassium is getting extracted with crown ethers. So they tried with other salts also, and they found out that even with colorless salts of, like for example, KCl, they found that potassium is getting extracted, and to neutralize the charge in the organic phase, the anion also goes along with it, and this is stable, and this is stable. So these are some of the classical examples which we read, which we understand as far as ion association complexes are concerned, and this is how uh, one can extract cations from aqueous phase to organic phase. And the other thing which I'll be possibly starting maybe next time when we meet on Monday, the metal chelates. Now this is a very very well known now mm, uh, reagents which are being used to extract cations from aqueous solutions, because the stability is very high, very high. So here what happens in ion association, the stability is not as high as, but these are some of the classical examples which have very high stability. They are highly stable in the organic phases, whichever phase is being used, whether it is isobutanol or diethyl ether or methylene chloride. They are stable. They are stable. But all such, one cannot extract all such ions, cations by such solvents. Everything is not extracted. So definitely you need some other ways to extract. And in that case, metal chelates is the best option, which we will be इसको भी हम समझेंगे आगे जाके कि metal chelates जब बनते हैं तब metals जो हैं वो organic like हो जाते हैं, bulky हो जाते हैं, covalent character आ जाता है, and therefore they go to the organic phase. तो मैं अभी यहाँ रोक देता हूँ because आपके मेरे बाद भी किसी का lecture होगा आपका. I hope you have understood today.
Yes, sir.
Yes, sir.
Okay.
But I
Any?
the ion association complexes where you have given those examples. In the first one, we used diethyl ether.
Yes.
So, in the extraction of iron, is it compulsory to use those substances, or it can be substituted with another or something?
Okay, you have a very valid point here.
Yes.
Now, as I said, that this is a very specific case. So here there is no chance of substituting diethyl ether in the extraction of iron 3. So if you wish to use toluene, for example, this doesn't happen. This doesn't happen. So as I said, these are very specific examples, and one cannot alter anything in this. One can try with other ions as well, but you don't get this much success as what was obtained with iron 3, and that too with diethyl ether. And likewise with univalent ions, which were extracted with in the nitrate medium in isobutanol.
Yes,
There also you cannot substitute isobutanol with say for example hexane. No, that you cannot do. So that is why I said there is a limitation to ion association complexes. They do not have wide applicability, and these are unique associations, and which may not be possible with other solvents for these ions or with other cations with these solvents. So yes, here we cannot change.
Okay, sir.
There are many options in metal chelates, but we don't have options in ion association. But this is just for your knowledge and information that yes, this also does happen. Okay, anybody else? अभी किसका लेक्चर है आपका अब? हेलो?
Yes, sir. There's no lecture, I guess.
There's no lecture. There must be the third one. Yes, third. नहीं है आज?
Archana ma'am, I guess.
ओके अर्चना मैम, लेक्चर अर्चना मैम का नहीं होना चाहिए बिकॉज शी इज नॉट देयर इन HPP, ओनली इन प्रैक्टिकल्स.
Ma'am, Wednesday, sorry sir, Wednesday there's only one lecture of yours, I guess. Is it Thursday or Wednesday? हाँ.
आज ऐसा का लेक्चर है सर, सो मैसूर सर ने ट्रांसफर किया हुआ है, बट सर लेक्चर लेंगे कि नहीं वो मालूम नहीं है.
हाँ,
अच्छा
exactly.
अच्छा अच्छा, ओके ठीक है. I'll just stop because if he would be there, maybe waiting, so I'll just stop and we will meet again on Monday. And but yes, yes, we'll meet on now Monday. Yes, yes. Thank you.
Thank you, sir.
Thank you.
थैंक यू सर.
Thank you. Thank you.
Thank you, sir.
Thank you.